Okay, grade 11s, here's the second half of your morning lesson. So this one is all about exponential decay. If you found the second handout, you maybe already looked at these questions. If not, I will read through them anyway, so that's fine. So here we're going to be using exponential functions to model and solve problems involving decay. The first one is an atmospheric pressure question. And the idea here is that as your elevation increases, like going up Mount Everest, for example, atmospheric pressure drops following an exponential pattern. So the pressure in the atmosphere decreases about 12% for every 1,000-meter increase in elevation. Okay, so every time you go 1,000 meters higher, there is 12% less atmospheric pressure. At sea level, air pressure is approximately 1,013 hectopascals, HPA. The atmospheric pressure is given by this function. So A is for atmospheric pressure after a number, like your elevation number. And we're going to try to break apart what are all of these values that show up in this equation. So I haven't yet shown you the exponential decay general formula, but we've seen the growth, so we'll see what we can figure out from here. So the 1,013, that was given in the question as the pressure at sea level. So I'm going to call that initial pressure. And if you'd like, you could say at sea level. And then the higher up we go, the lower the pressure is going to fall. The next one that shows up in the equation is 0.88, and that's the base of the power. That's the thing you're multiplying by again and again and again. And that's linked to either a growth rate or a decay rate. And here we're talking about decreasing pressure by 12% all the time. So we're taking away 12%, we're taking away 12%, taking away 12%. So we're doing like a repeated decrease of 12%. What's a little bit weird about this one is that the percent in the question was 12, and the number we see in the bracket is not a 12. So it's not 1 plus 12%, it's actually 1 take away 12%. That's showing up in the equation there. In decimal form, that looks like 1 take away 0.12. And yes, that works. That answer is 0.88. Okay, so the base of the power isn't how much pressure we have lost. It's basically saying what is our new pressure, or how much pressure do we have left. So the percent of air pressure remaining when we get up to our new elevation. So like 88% of it, 88% of it, which is less than 100, so it's decaying or decreasing. The last one there, this one has something in here different from our previous questions. Here the exponent is a fraction, which is kind of weird. In the last ones, the growth questions, the exponent was just the letter n, and that told you how many growth periods there were. So the answer to this fraction is the number of growth periods, or number of growths or decays in this case, to the number of times that's happened. And this one's kind of neat because it says it happens every 1,000 meters. So every 1,000 meters. That means if we go to an elevation of exactly 1,000 meters and fill in 1,000 for n, the exponent will be 1, and we would have lost 12% of the pressure one time. If we go to an elevation of 2,000, so 2,000 would be the n value, 2,000 over 1,000 will give an answer of 2. So we would have two decay periods, an exponent of 2, and we would have decayed twice by 12%. So the 1,000 in the denominator is helping us figure out the size of, so this wording is going to be maybe not perfect, but the size of a decay step. So step is not really the right word, but hopefully you know what I mean. So every 1,000 meters. N is going to be the elevation. So I was giving examples of 1,000, 2,000, 3,000 for the elevation. And together, those give us the number of the growths and decays. In this case, decays. Okay. So there's a lot packed into that formula that we had to kind of pick apart. But now these questions should be pretty straightforward. What would the pressure be on the roof of the Empire State Building? So at an elevation of 381 meters. So our elevation, hey, that's N, that's going to be 381. Atmospheric pressure at 381 meters. And I'm just copying the rest of that formula. And this will be 381 divided by 1,000 will be the exponent. I'm going to simplify that a little bit before grabbing a calculator. 0.88 to the exponent, and this is going to be 0.381. So that's kind of weird, but we can type that in the calculator. This is meaning we haven't yet gone up a full 1,000 meter elevation increase. We've done it less than 1 increase. That's okay. In your calculator, you're first going to do the exponent part. Come up with an answer for that, which is approximately 0.95246. And then multiplying that number with 1,013. The pressure is approximately 965 hectopascals. So I'm including units there in the final answer, even though I don't have room for the Air Force statement. Okay, so we started out with a pressure of 1,013 and now it's down to 965. So the pressure has dropped, which is what it's supposed to do. Yeah. Alrighty, so there is a second part to this one. What would the pressure be on the top of Mount Everest? So this first one, the Empire State Building, you've increased the elevation, but not by a lot. What if we went up high? So way to the top of Everest. So this is like an identical question with just a new number to substitute. 8,848 as our new elevation. Um, 8,848. Again, we're going to evaluate the exponent part of that first. And that answer is whoops, 88 to the exponent 8848. Oh, my calculator is not letting me do it. What's going on here? I'm going to grab my on-screen one. 0.88 to the exponent. Oh goodness. Okay, I forgot part of the equation. That's why. I forgot to do divide by 1,000. Okay, so the new exponent, 8,848 divided by 1,000 is going to be 8.848. I'll explain in a second why my calculator was mad at me. But first I'll type this one in. 0.88 raised to the exponent, 8.848. That's working out a little bit nicer. 0.3226688. You can keep like a couple of extra decimal places beyond what you feel you're going to need at the end. And then in the final answer, you can always round off. So we're going to multiply that by 1,013. And I'm looking at 327 hectopascals. Okay, so I was able to catch a mistake in my own work here. I had forgotten to divide by 1,000. So my exponent was huge. So this was multiplying a fraction or a decimal by itself almost 10,000 times. And the calculator was saying, hey, that number is so tiny, I don't know what to do. You've got next to nothing left. Yeah, so it didn't like that input. Anyway, I fixed that. I remembered to divide by 1,000 for this one and realized that if at an elevation of 8,000 meters, really we've gone up 8 chunks, 8 1,000 meter chunks. Alrighty. The next slide has the general formula. This is going to look familiar because we just did this with exponential growth. And I'm just going to point out that we need the initial amount. This time it's a decay rate. And this time we're using a subtraction in that general formula instead of an addition. The rate of decay is a number between 0 and 1. The question we just did was a perfect example of that. Or 88%. So between 0% and 100%, if we're thinking in percent form, or between 0 and 1 if we're thinking in decimal form. Everything else about this formula is the same as growth. Alrighty, so we're going to do 2 more questions. And the next one, we're going to have to come up with the formula on our own. And then the last one, we're going to have the help of a graph. And they're all going to be decay. Alrighty, so the value of a $21,000 car depreciates, oops, that's repetitive, depreciates by 2.3% every month after it was purchased. So you're losing 2.3% of the value every month. Write a function, v at n, so value depending on n, that tells how much the car is worth after a period of n months. So value after so many months. So we're going to use our general formula. I'm going to copy it out here so we don't have to flip slides. The general one used p as the variable. We can change the letter anytime we like. And we're going to try to make that our own in this question. So this says write a function v at n. So that's how I'm going to start. And then I'm going to build the right-hand side using numbers from this question. So P naught is like the initial amount or the initial value of the car, 21,000. In brackets, I'm going to have 1 minus the interest rate converted to a decimal. So I'm going to bump the decimal back 2 spots. Then I divide by 100. Now it's in decimal form. And just to tidy this up, we can simplify the bracket. One takeaway 0.023 is 0.977. So the idea here is if you're losing 2.3% every month, you still have the other 97.7% of its value. So this is like what's remaining. And this is the lost value. So those should add up to 100%. Okay, part B, evaluate. V at 12. So N in the brackets, that was the number of months. So we're doing 12 months, it looks like. And we'll replace the exponent with a 12. Again, we need to evaluate the exponent part first. 0.977 raised to the exponent 12. Um, 0.75637, and then we'll multiply that decimal answer by the initial value, 21,000. That gives 15,883. Because this is value of a car, I'm going to make it look like money by rounding off to 2 decimal places. So the follow-up to that is, what does this number represent? This is the value of the car after 12 months. If you want, you can put units there as well. This is dollars. Okay, so in that question, there was information given in the question, and we turned that into a formula that we could then use to find a specific answer. All right, there's one more question. And this one is kind of like a chemistry theme. And I think I mentioned this one during our brainstorming before spring break. So this one says, examine the graph below of the decay of a radioactive substance over time. We're going to be estimating the half-life and doing some other stuff. So I've just added a picture to this slide and a definition for half-life, in case that's not something you've heard of before. So half-life is the time it takes for half of a radioactive substance to decay. So the example here, this is cobalt-60, which is radioactive. At time 0, we're starting with 10 grams of it, or 100%. And then it's going to decay over time because it's radioactive and it's turning into something else. So after some amount of time, you're down to 50 grams, or 50%. At some later time, you're down to 25%, 12.5%. So half again. So these are half lives. And this is like one half-life for cobalt that happens to be 5.27 years. So every 5.27 years, the amount of it's cutting in half. Hopefully that little story made sense, and we'll do a similar one here in our real question. Okay, so in our graph, we're starting with percent remaining of a substance on the y-axis. So these are percents, just to keep reminding us of that. We're starting with 100% and dropping. The horizontal axis is looking at time in years. So this is very different than the cobalt example, decaying every 5 years. This is looking at like a long time scale of thousands of years passing. So this is obviously a more stable isotope that doesn't decay so quickly. And we're going to estimate the half-life of this element. Okay, so just to remind you over here, the idea is that one half-life is the amount of time it takes to end up with half of your original material. So we're starting with 100%. When we are down at 50% left, how much time has passed. So we can look at the time axis to find that. This was the 2000, 4000, and the 6000. So we're looking at 500, 500, 1000, 1500. 1500 years. So this is 50% remaining, which is exactly what I was looking for, half of it. And the time that that corresponds with is around 1500 years. Okay, use your answer from part A to find a formula for the percent remaining. So it's going to have the same kind of structure. I'm going to give a little more space for this one. It's going to have the same structure as the general formula. So I'm going to copy that out for us to refer to. We need to know the initial amount, the decay rate, and we can leave this as a variable. So the percent remaining after, this says to use t for time instead, after some amount of time. We started out with 100% of our material. We are losing 50%, which I'm going to change to decimal form. We're losing 50% each time, or half. And this is time. Actually, I'm going to be a little bit weird. I'm going to leave this as n, the number of decay periods. And I'll explain in a second why I've done that. Okay, so there's two things that can be changed here. The bracket can definitely be simplified, and I've got to do something with that 1500 years. Like, how does that fit into this picture? So I'm going to include that in this next step. So we're starting with 100%. One takeaway 0.5 is 0.5, or get this, half. So weird to change from decimal to fraction, but half-life, half as the base. We can start with that from now on, knowing that the base is going to be a half for a half-life question. And the exponent is the number of times we have decayed. So 1 decay period, 2 decay periods. But we also need to link in the 1500 years. So I'm just going to do that for you here. Time divided by 1500. And help you notice that this is really similar to the atmospheric pressure question that had a fraction in the exponent. In that one, the pressure was decreasing every 1000 meters. And in the numerator, we were plugging in our elevation in meters. So a distance divided by a distance gave us like an exponent that was just a number with no units that told us how many times it had decayed. This is going to be the same thing. So if the time elapsed, or the time that has passed is 1500 years, then we're talking about this first decay, 1 half-life. If the exponent, or if our time is 3000 years, so let's look at this one, 3000 years. Now we're down to 25% of our material. So we're down to half again. If we look at 4500, a time of 4500 years, then we're down to, it's hard to see on here, but this is 12.5%. Right, so that fraction exponent helps you kind of include a little bit more information. All right, last part of this, use the formula to determine to the nearest percent the amount of this element left after 9,000 years. So 9,000 is going to be our p-value, the time. So the percent left after 9,000 years. If you don't like the fraction 1/2, you can keep it as a decimal 0.5. You can even like go back and forth between them, depending on what your preference is. If you're about to punch it in a calculator, the decimal might be better. But 9,000 divided by 1,500 is my exponent. So that's the first thing I'm going to simplify. Let's see, 9,000 divided by 1,500 is 6. So 9,000 years is 6 decay periods. 0.5 to the exponent 6 is 0.015625. And multiplying those two together just shifts the decimal over 2 spots. So we're starting with 100%. We are finishing with only 1% after 6 decay periods. So we can look at a graph and see if that makes sense. So we're after 1 decay period, we're down to 50%. 2 decays, we're down to 25%. 3 decays, we're down to 12. 6, 3. Oh yeah, we are down at 1.5% down there. So we're just kind of extrapolating that a little bit farther to the 6th decay period. Okay, so there's our last problem. So there is a worksheet with a little bit of growth practice mixed in with decay practice. There's answers at the bottom so you can check as you go, and I will be available during the help session. You can log in and ask anything either about the lesson or about the worksheet questions if you need any help.